All right, let's get right into it. Today, we're unpacking a story that seriously sounds like it was pulled from a sci-fi novel. We're talking about a material, graphene, that did something so strange it made physicists rethink a law they've leaned on for over 100 years.
So this was the headline that just stopped everyone in their tracks. And look, we're not talking about a tiny little error margin or some small adjustment. The claim here is that graphene, yep, that super famous one-atom-thick wonder material, did something that, by all accounts, should be completely impossible.
So that's what we're here to figure out. How exactly did this law get broken? We're going to investigate the scene of the crime, we'll look at the broken rule itself, and then we'll dive into a new theory that doesn't just solve the puzzle, it suggests that this little graphene experiment just gave us a direct window into a much, much deeper level of reality.
Okay, first things first, what exactly is this so-called fundamental law that graphene supposedly just smashed to pieces? To really understand the crime, you gotta understand the rule that was broken. Here it is, the Wiedemann-Franz law. Now, for about a century and a half, this has been a solid, reliable rule for pretty much any normal metal you can think of. It basically says if something is good at conducting electricity, like copper wire, it's also going to be good at conducting heat. It's why a metal spoon in your hot coffee gets hot all the way up the handle, right? The two things are supposed to be locked together.
And the reason the law works, well, it's actually really simple. It's because the same tiny particles, the electrons, are doing both jobs. They're carrying the electrical charge from point A to point B, and at the exact same time, they're carrying the heat energy. And since it's the same particle doing both things, it just makes sense that whatever slows down the electricity would also slow down the heat. Simple enough, right?
So now let's go to the scene of the crime. This whole mystery takes place in what's called ultra-clean graphene. Under just the right conditions, it stops acting like a solid material and morphs into something else entirely. A bizarre, exotic, almost perfect fluid made of pure electrons. In this state, scientists saw three incredibly weird things happen all at once. First, the Wiedemann-Franz law didn't just bend, it absolutely shattered. It failed by a factor of more than 200. Second, the electrical conductivity became universal. Different samples of graphene all started showing the exact same value, like it was programmed by some new law of nature. And third, this stuff started flowing like a nearly perfect fluid, with almost zero friction. Any one of these findings is strange, but all three happening together? Well, that just screams for a whole new explanation.
So here's where it gets really interesting. In a normal metal, you've got this sparse gas of electrons just kind of bumping into random imperfections in the material. But in this graphene Dirac fluid, it's a completely different game. It's a thick, soupy mix of electrons and their opposites called holes. And in this soup, the particles are almost exclusively colliding with each other. This fundamental change is the key. It's the reason that lock between heat and charge just completely falls apart.
So how in the world do you explain all this? Well, the answer seems to come from a totally radical new way of looking at physics. It's an idea that suggests our universe isn't some smooth, continuous thing, but is actually built on a discrete geometric grid. And out of this framework comes a wild solution. It's not that the law was broken, it's that we were measuring two completely different things all along. And this right here, this is the light bulb moment. The model asks, what if you just forget the idea that one current is doing two jobs? What if, in this special graphene fluid, heat and charge are being carried by two structurally different types of currents, each flowing through its own separate channel? Okay, so let's break this down because it's the key to everything. First, you have the signed charge current. This is what we think of as electricity. It cares about positive and negative signs. And in that dense soup of electrons and holes, it's like a constant tug of war. The positive and negative charges are moving against each other, crashing and canceling out. It's a frustrated flow, and it becomes really, really weak. But then you have the unsigned heat current. This one is just carrying raw energy. It doesn't care about plus or minus signs, so the electrons and holes can work together, like a huge crowd all running in the same direction. This flow is assisted, which makes it incredibly strong and super efficient.
So once you have this two currents idea in your head, those three baffling experimental results, they suddenly just click into place. Let's walk through how this one single concept solves the entire mystery.
All right, first up, the big one. Why did that century-old relationship between heat and electricity just completely disintegrate?
And boom, here's the answer. The law fails because we were comparing apples and oranges. The electrical current, the signed, fragile one, is getting choked off by all those cancellations. But at the same time, the heat current, the unsigned, robust one, is flowing like a champ. So what you get is terrible electrical conductivity, but amazing heat conductivity. The ratio between them goes completely haywire, and that old law, well, it just doesn't apply anymore.
Okay, on to puzzle number 2. Why did every piece of graphene suddenly start conducting electricity at the exact same value, as if it were magically tuned?
According to this new model, the answer is just mind-blowing. The flow of electricity is no longer limited by random little defects in the graphene itself. Instead, the flow is tapping into a fundamental property of the universe's underlying grid. The conductivity becomes universal because the discrete tetrahedral lattice of space-time itself dictates that this is the only value possible. The material isn't just acting weird, it's literally revealing a fundamental constant of reality.
And that brings us to the third and final mystery. Why was this electron hole soup flowing with practically zero friction?
Well, this ties right back to our two currents. That super robust, unsigned heat current isn't just strong, it's incredibly efficient. It has found the absolute path of least resistance through the fabric of reality. The technical term is a low inversion burden channel, basically an easy street that lets it flow with almost no effort, which we observe as nearly frictionless fluid motion. So the low viscosity and the high heat transport, they're really just two sides of the same coin.
So, okay, the puzzle is solved, but honestly, the implications of this solution go way, way beyond just explaining one weird experiment. This could fundamentally change how we think about physical laws themselves.
Here's the big picture takeaway. First, a lot of our physical laws might just be descriptions of specific conditions, or regimes. Move out of that regime and the law simply stops working. Second, it means that reality has these hidden complexities, like these two different types of current, that are usually fused together so we can't see them. And third, and this is the part that should give you goosebumps, graphene in this special state isn't just a metaphor, it's a direct interface. It allowed us to see past the smooth illusion of spacetime and directly observe the raw, discrete mechanics of a deeper reality, a reality governed by token-like exchanges on a fundamental lattice.
This quote from the researchers who wrote the paper just says it all perfectly. Graphene in this experiment wasn't just some weird material. It became a lantern. It lit up a fundamental difference in how energy flows at the most basic level of existence, a difference that gives us the first real experimental proof that we're living in a discrete, computational universe.
And that's the question we're left with. The Wiedemann-Franz law wasn't really a law of the universe. It was just a law of a particular state of matter. So, if some of our most trusted rules are just emergent patterns, just shadows cast by a deeper, hidden, and discrete system, what other fundamental laws are just waiting for the right experiment to reveal that they, too, are just reflections of the true reality underneath it all?